Right, guys, yesterday we introduced complex numbers, and I believe that we went as far as division. Now, just some few things just before we go on with our topic. Let's do this. Now, when we did division, I would highlight that this notion of conjugate is very important. Conjugate of a complex number. What's sorry, that's a bit ugly. Let's say conjugate we're talking about the conjugate of a complex number here. Right. The notation for this conjugate is as follows. If I've got Z, a complex number, I write a bar there. I just write Z bar. When I read that, I read it as conjugate of Z. Are we making myself clear? Okay. So if Z is 5 minus 2J, then I'll write this as conjugate of Z equals to 5 minus 2J, then I put a bar there. And then what is this equal to? Then this is equals to 5 plus 2J. Am I making myself clear? Okay. So I think, notice one thing here. Notice one thing here. If you are talking about a conjugate, if you are talking about a conjugate of a complex number, complex numbers are represented on a plane. Then let's say here I've got 3 plus 2J on this side. Conjugate, you change this sign. In other words, instead of talking about 2J here, you talk about minus 2J there, which means this number is going to be flipped across or reflected across the x-axis, which is this one, and then comes here the 3 minus 2J. So what I'm trying to say is that conjugate numbers sit across the x-axis, same distance apart. All together. That is very important. Now it's similar to if you're only dealing with the number line, the real number line, then we take 3 and minus 3. We don't normally say those two numbers are conjugates, but we normally say they are additive inverse. And if you look, they sit. What is the reference point when on the number line? The reference point is what? Is 0. So they sit across that thing. But then when we start talking about the plane, the x-axis divides the plane into two halves, the upper half and the lower half. So in the upper half, there's a number, complex number. In the lower half, there's this conjugate. Am I making myself clear? Okay. So let's go on there. Now let's play a little bit here with the conjugates. Let's play a little bit with conjugates here. Right, also let's just play a bit with conjugates, numbers. Let's take Z1 here to be 2 plus 3. And then the conjugate of Z1 to be 2 minus 3j. Now, but before I do that kind of playing around these numbers, let me also introduce another a notion here of the modulus of a complex number. And this is not strange to anyone who has done vectors. Let's roughly put a system of x's. There is a complex number x plus iy. That's a complex number, and there I've given also its vector kind of representation. Then if this is z as a complex number, then we denote z, we denote this way the absolute value of z. That's the absolute value of z. Exactly the same way we did with vectors. We project this point down here, we've got x here. We project that point there, we've got y there, and actually this is also y. We get a rectangular, a right angle triangle, sorry. Then using Pythagoras, the absolute value of z is this hypotenuse there, what you used to call r. So you can actually say r equals to absolute value of z, and everybody knows that using Pythagoras, this is x plus y and the absolute value. That's right. And that is a positive magnitude. Now this is greater or equals to 0. When is equal to 0, we've got the complex number. Check this. If this is equal to 0, it means that you've got the complex number 0, which is equal to 0 plus I 0. What is 0? 0 is a real number, is it? But 0, I can write it as a complex number as 0 plus I0. Here at this point, I think everybody must see that every real number is a complex number. Is that clear? Now I'm saying every real number is a complex number. That's the symbol we use for complex numbers. Why? Because if I've got 2 here, I want to give it its complex kind of picture. 2 as a complex number would be 2 plus 0 j. All together? Okay. Then when I'm talking about 2j, I'm talking about a number, a complex number, which is a pure imaginary number. Then if I'm just talking about 2, I'm talking about complex number, which is a real number. So what I'm trying to do this thing, I'm trying to show you that complex numbers are just expanding the family of numbers without throwing away any of the numbers we've seen before. Am I making myself clear? Am I making myself clear? Okay. Right. So let me do this. I want somebody to tell me what is this. Let's say I wrote here r squared. What did you say that is? Isn't that the absolute value of z squared? What is it equal to? It's equal to x squared plus y squared, isn't it? So even if now I say now find the absolute value of z1 squared, you'll get it, isn't it? Quickly calculate it and tell me what it is. The absolute value of z1 squared. So calculate it first, don't just announce anything, calculate it first. Have you calculated it? Yes? What is it? Absolute value of Z1 will normally be 2 squared plus 3 squared, isn't it? That's what's that? 4 plus 9, that's 13. Square root of 13. So that's square root of 13. Now, what's the absolute value of Z1 squared? 13. Okay. So please, I would like you now to multiply Z1 multiplied by Z1 bar. Can you please do that? Right, 13 is the correct answer, but let's check those guys who didn't correct the correct answer. Are you correcting your mistake? Did you find your mistake? Please, try not to make the mistake again. This is a fact of life. You can write it as a theorem or whatever. It's a fact of life. If you multiply Z1 by Z bar, now the number by its conjugate, you will always get the absolute value of that number squared. Even if you think that now we just did it with x and 2 plus that in the particular case, then try to do with a z, which is x plus I, y. Then find the conjugate of this number and then do exactly the same thing. If you don't get x squared plus y squared, then which means there are no complex numbers in the world. Are we fine, guys? Okay. So I think all this, why I'm talking about conjugate, because we use the conjugate way in division altogether. So immediately I wanted to make you aware of some facts around this number called the conjugate of a number. But in this case also notice that the modulus of Z1 is equal to the modulus of Z1 bar. In other words, the conjugate, a number and this conjugate, they've got the same magnitude. That's a property also you need to be aware of. My friend, you know I don't like that kind of question in my class. Right. Can we go on now? Okay. Then let's, I think I'm going to move away there now and let's come to another part of our work. Now, this is graphical representation of complex numbers. I think this is a repetition of some kind because from the beginning, it looks like complex numbers and the system of coordinates are almost very close to each other. So then, if I take sorry, let me take a pen first. If I take a pen and put a point there, because now points on the system of coordinates or on the plane are represented are pictures of complex numbers. Does everybody understand that way? Okay, so now this number, who can tell me what this number is? If you can see on the board. This number is 2 plus 3j. Now, as I've represented there, is the same way I've represented 1, 2, 3, 4 on the number line. But now this is a complex number. I've represented this number where? On the plane. All together. Okay? Then I maybe can want to represent a number, a complex number, as a kind of a vector. Then I do this. Do you see that? I lift my, and then I say, what number is that? minus 4 plus 3j. So when I'm doing that, I'm saying I'm putting a number, I'm representing number graphically. That's what you say there. And the result to present it graphically in a system of coordinates like this, I can interpret it as a vector, I can interpret it as a point, I can even interpret a complex number as an ordered pair of numbers. As an ordered pair of numbers. And this pair is not the same pair as 3, 2. So when I've got a pair, and they say this pair represents the complex number, the order is very important. All together. Where is 3, 2? 3, 2 will be somewhere here. Am I right there? That is 3, 2. And because you can see the 3, 2 and the 2, 3, they are different numbers. Am I making myself clear there, guys? Is there any question you want to clarify? You are comfortable with this? Okay. Now, yes. So, what next? Are you sure you don't have questions? And every number present here, you must be able to see where is it conjugate, how could I calculate this modulus, and all those things. And those things are already been discussed. Are you writing something? Okay. Okay. Then I also want to sort of talk about addition of these numbers. Addition of these numbers. Let's say, let me maybe clean up this one. We know the number I've got here. What is this number? It's 3 plus 2j. Now let's talk about this number. This number. I put it dotted there as a dotted vector. You can see it. It's different. What is that number? 1 plus. So that number is equal to 1 plus 2j. And here I've got another number. Let me call it Z1. And then this number is 3 plus 2j. If I were to add these numbers, Z1 plus Z2, let's start by adding them geometrically, as they are represented geometrically. What did I do? I will take this vector, I'm trying to move this vector, but I don't know why it's so difficult. Okay, let me do it again, maybe just reproduce that vector, because it doesn't want to move. It's 1, 2, so that vector will go that way. Do you agree? Now the new vector will come from here, the origin, to that. What is the vector there? Geometrically, what do you see? On the geometrical representation, what do you see there? 4 plus 4j. Let's take it this way. Arithmetically, these are the values. That will be equals to 1 plus 2j plus 3 plus 2j. Adding those two, like we did yesterday, we're getting 4 plus 4j. As you can see now, I'm trying to be fast now because today I'm expecting to have experience now of what is happening, isn't it? Yeah. So that's this thing. So what does it mean? Whether you add this number geometrically or you add them arithmetically using the numbers themselves, you get exactly the same answer. All together. Now what I want you to do, I want you to multiply two numbers. Simple numbers, don't get numbers with big values here, just two numbers. And I want you to check what is multiplying two numbers. What happens on the system of coordinates here? That's an investigation which you're supposed to get to point to. Now, right. The other thing we have here, I think maybe that's the next discussion we must do. That's the next discussion we must do. What's written there? It says polar, rectangular, polar, and exponential representation. Let's forget about the last one first. Let's talk about the rectangular and the exponential representation. Now check. Let's have Z1 there. Who can give me Z1? 3 plus 4j. Let's calculate the modulus of that number. Are you getting ready with your modulus? Who is ready? What's your modulus? 5. I'm not going to really, I've checked it also is 5. So I hope everybody follows how to get that 5. Is anyone stuck? No one. Okay. Now, notice that that number, like any other complex number, like any vector on a 2-dimension, will always form an angle theta between the x-axis and its arm there, or the vector. Am I making myself clear? Okay. Then that angle is important also, because remember, as a vector is characterized by its magnitude, which is this one of character, and it also characterized by the direction, and the direction is given by the angle. All together. So then that angle is always given by the second function tan. Come again? Second function tan y over x. I'm writing general here that for any number it will be like, isn't it? Then you can calculate it for our particular number here. Our particular number is 3 plus 4j. Now it's going to be 4 over 3. What am I taking here? I'm taking what I called yesterday imaginary part and real part. So we're taking the imaginary part of Z1 and the real part of Z1. Is that clear to everybody? Okay. So now it's very important. I talked about this yesterday. So it's very important to be able to extract those components of the probability number so that you can work with them wherever you want them. So that is the angle. I'm not really interested in what is the size of the angle. I don't even need a calculator here. So now, notice one thing which is very, very important. You cannot separate this angle and this number from the complex number. There's no way you can tear them apart. I hope you understand what I mean by that. There's no way you can have that vector or that complex number 3 plus 4j without having that 5 and that with having that arctan of 4 over 3. Are you listening to me? Are you hearing what I'm saying? Take a 5 rand coin. Everybody listen to this thing will know that we're in South Africa. And there's no other country in the world which is like South Africa. If you didn't know, you learn it through there. If you find it, that is South Africa. So you take a 1 rand coin, try to separate the head from the tail of the coin. Do you have a 5 rand coin? No. Those things are inseparable. For that thing to be a coin, it must have head and the tail altogether. For this number to be a complex number, it must have the angle, it must have the modulus. So those are characterizing elements of the complex number altogether. So you can forget anything else and hold on those ones. We're not going to lose on a complex number. What do I mean there? I mean that having Z represented as 3 plus 4J, that is Z1 on the graphical representation. This number, I can represent it by only 2 elements. The modulus and the angle. In some cases, this is how we represent it. You say R angle theta. Are you hearing what I'm saying? Then what is this now? What is this? This is what we call the polar representation. These numbers R and theta as an angle, they are called the polar coordinates. Those are polar coordinates. What is X and Y? X and Y are called the rectangular coordinates or Cartesian coordinates. So what can we say? I can say, or we can say, we can write a complex number in 2 different ways at the moment. One, in rectangular form using X and Y. 2, in polar coordinates using R and theta. Am I making myself clear? Please guys, if I'm not making myself clear, you say it in capital letters. I'll repeat what I'm supposed to say and I try to say it better. Anyone who is not wondering or not understanding something, you want to say something? Yes, ask. That's why I'm been asking.
You took the rectangular to get the polar form. Is it possible to take the polar form?
Very good. What do you think? Somebody else, what do you think? It is the same. Your friends are saying it's possible. Altogether. Good. That's exactly where we're coming to. Let's take this back to trigonometry. We said sine of any angle theta is y over r. This is exactly equivalent to saying y is equals to r sine theta. So if you're holding only on r and theta, you go back to y by doing this. Are you there, my friend? Do you understand? Are you following what I'm saying? Okay? Then similarly, cosine, which is the horizontal axis, on the horizontal axis is x. This is x over r. This tells you that x is equal to r cos theta. What is this? What is this thing saying? He's saying, why do we have to have a number written in polar coordinates, in rectangular coordinates? It's all about convenience. You might find that in one situation, it's actually more amenable for you to work in terms of rectangular coordinates. In another situation, it's more favorable that you work with polar coordinates. Altogether. Yeah, my friend. Why do you look like you are You are surprised. Is anything surprising you? I'm talking to you. Why are you looking at me? Because your face is telling me something which I don't understand. Are you fine? You okay? Yeah, but you must, if you are okay, you must be jovial and happy and looking happy, but you don't look happy to me. Are you fine? Okay, good. Oh, my voice is intimidating you. What's happened? Huh? Don't worry about this voice. It goes up and down. Depends on the situation. Right, guys? Is everybody fine? So that's what we're going to do then. Are you sure you're fine? I'm not hearing anything. Okay. You know, it really, I know, I told you before, I'm somehow an abnormal person. Sometimes I don't feel very comfortable when I talk to people. They just behave like in a very fun way, like I don't know what's going on. If you're understanding, you must say it very lively. Yes, we're getting this. If you're not understanding, also say it very loudly. No, what is all this about? What are we talking about? We're talking about rectangular coordinates and polar coordinates, isn't it? Okay. Now, I would like to appeal to everybody to accept what I'm writing here now as God-given. What am I saying? Every time when I'm going to say, let's take this thing as God-given, maybe it's involving some maths which you haven't learned and we are still going to learn, but it's something which I need to exploit for some minutes and to get me moving. So don't ask for proofs for these things now. I'm saying we're going to learn them later. Are we together? Okay. Right. What are we going to take as God-given here? We're going to take as God-given that the exponential number elevated to power x can always be written as 1 plus x plus x power 2 over 2 factorial. I will explain immediately now what I mean by 2 factorial. I know that you don't know that. Plus x to the power 3 plus all over 3 factorial plus x to the power 4 plus 4 factorial plus dash dash dash. That continues. This is God-given. Also God-given, sine, the usual sign we know, sine of x is x minus x to the power 3 over 3 factorial plus x to the power 5 over 5 factorial minus x to the power 6 over 6 factorial. Let me apologize a bit for something here. I'm not really sure whether my signs are correct. I'm talking about plus or minus, isn't it? But if they're not correct, I will realize. But my memory tells me they're like this. I thought about this yesterday. I said I was just going to check these signs, but I never checked them. But if they're wrong, I will realize that they're wrong. I will correct it. Is that right? So apology for that. Says cosine x will be equals to 1 plus x squared over 2 factorial plus x to the power 4 over 4 factorial plus dash 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 dash. Are we together? Okay. Now, let me write something now strange now. I, J, theta. I want all of you, I'm inviting you, I'm not saying you're going to win this thing. I want to invite all of you, without doing any simplification, I want to write this thing here in terms of what you saw at the beginning there. Just repeat this exactly in terms of what you saw at the beginning there. Don't simplify anything. If there's a j squared, leave it as a j squared. If there's a theta j squared, just leave it as theta j squared. Are you getting what I'm saying? So, but rewrite this in terms of this kind of expression. Do it, everybody. Right. I think everybody wrote this way. Is that right? Without simplifying anything. But let's clarify this situation of n factorial. What is n factorial? N factorial is the product of n multiplied by n minus 1 multiplied by n minus 2 until multiplied by 3 by 2 by 1. No. Think slowly. Think slowly. N factorial is n multiplied by n minus 1 multiplied by the n minus 2 until I get to 3, 2, and the 1. What is then 5 factorial? It says is 5 multiplied by 5 minus 1, 4 multiplied by 5 minus 2, 3 multiplied by 5, and then it comes 2, 3, 1. That is what we call n factorial. It's not important now. I'm just trying to ease the things which we are not very comfortable with. But whenever somebody says n factorial, it means multiply these numbers. If you want, take your calculator and say 2 factorial to give you 2. 4 factorial, then do this kind of exercise. But you will see later, as we do our maths, where does it come from? Where do we experience this kind of a thing? All together? Okay. Now let's come back here. Let's come back to this. Let's now simplify. 1 plus theta j minus theta squared over 2 factorial. However, minus, no. Am I right here? Okay. Okay, here I'm going to have j and the j squared. J squared is going to give minus. So I'm going to have minus j theta cubed over 3 factorial. Here I'm going to have j squared and j squared minus going to be plus what? Theta power 4 over 4 factorial. Am I fine? I'm worried about this sign. I don't know why I'm worried about this sign. It's correct?
Yes.
It's a j squared. You get theta squared, j squared. It's good to give us minus, isn't it?
Yes.
Yeah, so it's fine. Now let's collect things with j and those things without j. Let's collect those things without j will be 1 minus theta squared 2 factorial plus theta 4 factorial plus dash 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 plus j let's take those entities with j. Theta minus theta over 3 factorial. I think here to be plus 5, plus theta to the power 5 over 5 factorial plus then dash dash dash. What am I trying to do? I'm trying to have 3 terms in each one of them, is it? Let's go back a bit here. Here. If we put 5 here, we're going to have plus j theta power 5 over 5 factorial. If we have here, we're going to have 2j squared. 2j squared minus minus, which is plus, and the j, which is going to give us theta that. Then we've got this last part here. All together. Do you agree on that one? That's a j. Okay. Now I'm coming back to my signs. This sign was wrong. You understand what I'm saying? I told you that if there's a sign which is wrong, I'll discover it. But I had to check this thing before. I didn't check it. This sign is supposed to be minus. Can you correct that, please? Everybody, please correct that sign. That sign is minus. I told you that I'm just working on this thing from my memory, and normally memory is not very good. But that sign is not correct. That's supposed to be minus. Now agree that that sign is minus, and those signs are correct. These ones are correct, and this sign is minus, and it will just go changing like that. Plus, minus, plus, minus, plus, minus. Now, let's come here now. What do we have here? What do we have here? We have got cosine theta plus j sine theta. What is this? It's a complex number. Remember, a sine of an angle is a number, isn't it? A cosine of an angle is a number. So this is a complex number. So this complex number, we are actually saying cosine is x, sine is y, but now we're saying this is equals to j theta. What are we saying? We're saying a number written like this can be expressed in exponential form. So this is exponential form of complex number. Now, what is not clear about this number now is what is the modulus of this number? Can you please quickly calculate it? What is the modulus of this number? This number is e to the power theta j. This is equal to cos theta plus j sine theta. What is the modulus of this number? What did you do? We take x squared plus y squared, you put in the square root. This is it. So what is the modulus? 1. This was then the test when we were calculating that determinant, which is the cos alpha sine alpha. You came up with cos squared plus sine squared, and it was equal to 1. And this is exactly the same thing. There it is. What is the conjugate of this number? The number is cos theta plus j sine theta. What's the conjugate of this number? You say this is equals to cos theta cos theta minus j sine theta. If you work it out properly in that expression, you will get that this is equals to e to the power minus j theta. Are we together? So guys, I'm now listening to you. any clarifications, any problems, anything which is not clear, this is the time to ask. If you don't realize what we have learned today, we have learned how to calculate the modulus of a number. We have learned that these numbers, you can represent them graphically, and they are basically pictures, or they are vectors if you want to have that bias. We have now shown that you can take them from rectangular form, where you are using only x and y, to polar form, where you are using the modulus and the angle. Or you can take it to exponential form. Now, any number complex number which is it doesn't have modulus 1 will be a number z equals to x plus jy. As you can see today, I'm using I and j, whatever. I think you can understand the problem, isn't it? So this number, we can calculate its modulus as x squared plus what? Y squared. Then this number, we can now take this number as r cosine theta plus j r sine theta. Are we there, all of us? Then we can factorize r and put r here and say cos theta plus j sine theta. What is inside here? What is inside here? What is inside here is actually E J theta. All together. What is outside there is R. So what am I saying? I started with the number only the modulus 1, but any other number in exponential form will come as modulus multiplied by E to the power j theta. And then what is this? Which is the same thing as number, rectangular form. I can even say here, number more or less between rectangular form and the polar form. Number in exponential form. Number, modulus, argument. This angle, actual theta, is normally called its name. This angle is called the arg z, meaning the argument of z. That angle is not normally called just angle. We will say calculate the argument of z. The exercise are basically going to come this way. Here is a complex number. Determine the argument. Determine the modulus. Write it in polar form. Express it in what? Using polar coordinates. All sorts of things. All those things you must be able to interpret what they mean there. And as you can see, I said it before. Things are accumulating. Words are increasing. Each word has got a meaning. If you now start to mix them up, I cannot come to class and say I'm going to teach only one concept today and only one word. No. That one word will be linked to other 3, 4, 5 new words. It's up to you to make sure that you organize yourself and make sure that you follow this thing thoroughly until you actually master the thing. As you can see, I'm not opening a book here. I'm not reading a book. Am I reading a book? No, I'm not reading a book. I'm just teaching this thing from my head. That doesn't mean that I'm bright or I'm special or whatever like that. It's because I've decided to sit down and make myself get used to these things. I wouldn't move as fast as I'm moving with this content if I was reading a book. But that does not come by just writing the notes and throwing them under your bed. It comes with writing your notes and sitting on the notes and just trying to embrace them and going to them like a sponge embraces droplets of water in a saucer. It just goes. So you must immerse yourself in these things. If you don't get the message, it's unfortunate, but that's what I'm saying. Yes, Lamin.
Yes, after asking the God-given sign and cause, the expression is supposed to go on exponential, like the first for sign, the first one is x, the next one is x cube, the next one is x.
Yeah, let me just explain that thing. We're going to do that thing when we do differentiation. I'm going to show you exactly how we come up with these God-given things as I've said them here. What I mean by God-given, I just say accept it as true. Is that right? Nobody would question something from God unless if there's something wrong with your head or something like that. All together. So you just take it as that. But this is temporarily. Let me put maybe in brackets there. Just temporarily, let's take this thing as God-given. But this is maths. There's obvious these things have got theories and proofs behind them, which you can work them out. But let me tell you something. Most in E will always come with powers 1, 2, 3, 4, and all the signs are positive. Sine will come up with powers 1, 3, and that. And that has got to do with the property of sine. Sine is an odd function. I think I will explain later what I mean by odd function if I've never explained before. And a cosine is an even function. When I'm saying a function is odd, I mean it's like a hyperbola. Take a hyperbola at minus x. It gives you a value which is opposite sign what it takes at x. Take a parabola, take it at minus x. It gives you a value which is equal to the, take it at minus x, it gives you a value which is equal to the value at x. Then the parabola is even. And the hyperbola is what? Is odd. And then cosine is even. It takes even number powers. Sine is odd, is not even, it takes the odd powers. So then the signs will change exactly like that. Positive, negative, positive, negative. But let's go to that when you get there. You'll see it very, very clear. Where is 6 way? Oh, I put 6 there. Sorry, that's a 7. Sorry. Good. I didn't notice what you're talking about. Yeah, that's a 7. 6 is supposed to be here, this side, this side. Good for that one. That I think that was just a slip of a pen. And as usual. I mean, if I won't do it that way, make a mistake like that, then I won't be a human being. I don't know what I would be. Okay, thank you for that correction. Thanks. This is what I like. People who engage with the content. You understand? We're talking about the content. In this case, what's that? The mathematics we're doing, we're writing on the board. Not on other things in the sky and above the moon. Okay. Thank you for that listening. See you when you see me. I think this time I've been